Okay, let's get going on a Gauss's law problem that has a little bit of a twist. It's not quite as simple as just a plain solid sphere. We have a thick spherical shell. It has uniform charge with density rho uniformly distributed throughout its volume. So the shell means that it's like I don't know, like a bowling ball, right? It's got a thick shell, but it's got an empty core. So inside here, this white space is just vacuum. There's nothing. This gray space is the shell, and then outside again, there's nothing. It's got density rho. Rho is your volume charge density. And that's total charge over total volume. Uniformly distributed, so as with any insulator, when there's charge, it stays where it is. So the charge is kind of little bits all over the place and it doesn't move around. The shell has an inner radius A and an outer radius B. The cavity within the shell is empty, so it's a vacuum. Find an expression for the electric field as a function of distance from the center of the shell, so as it depends on here. Begin with Gauss's law and show all steps. So we're going to try and find the electric field in three places. We're going to find the field somewhere in the white space, somewhere in the gray space, and somewhere outside everything. We're going to use Gauss's law, so let's write that down. Gauss's law says that the net electric flux is the integral of E dot dA, and that's equal to the charge enclosed by our Gaussian surface divided by epsilon naught. We have to pick what kind of Gaussian surface we're going to use. We have spherical symmetry in this problem because our charge is a spherical shell. So any kind of spherical symmetry, normally we would pick our Gaussian surface to be a sphere with radius r. So no matter which part of our surface we're talking about, no matter if we're under A, between A and B, or outside B, we're still going to pick a circle for our Gaussian surface. So let's do this part first. So my Gaussian surface is a sphere with radius that I'll call little r. Little r. Now, when I have spherical symmetry, the electric field is radial. So, whatever the electric field looks like, unless it's zero, it's going to be pointing straight outwards. Okay, so when we have spherical symmetry, electric fields point straight out. So let's look at what our E dot dA is going to be equal to. The integral of E dot dA is the integral of E times dA times the cosine of the angle between E and dA. dA is a little bit of the area of this Gaussian surface. That comes straight out because area vectors come straight out of surfaces. So E and dA are parallel. The angle between them is 0. Cosine of 0 is 0. When we're a uniform distance away from the center, our electric field is constant and it can come outside. So I've got E outside times the integral of dA times the cosine of 0, which is just 1. Integral of dA is A. That means the area of our Gaussian surface, which is 4 pi r squared. Okay, so no matter what little r we're talking about, this is the result we're going to use for this part of Gauss's law. Okay, why don't we start with r less than a. I'm going to draw a Gaussian surface first. So part A, r less than a. My Gaussian surface will be a sphere with radius r less than a. Oops, I labeled it a because I said a. There, that's an r. If r is less than a, the part that I have to figure out before I use my Gauss's law, what is Q enclosed? Well, Q enclosed equals 0. All the charge is out here in the gray stuff. This white stuff is nothing. It's just a vacuum. Q enclosed equals 0. Okay, we'll put together our Gauss's law. E times 4 pi r squared equals Q enclosed over epsilon naught E equals 0. Okay, the electric field inside our cavity is equal to 0. Next, we'll find the electric field between A and B. I got that sheet of paper filled up. We'll just grab another one. So for my electric field between A and B, so I've got A less than R less than B. I'm going to draw a Gaussian surface. My Gaussian surface is a sphere with radius that I'll call little r. So, just as I found my Q enclosed in part A, I've got to find my Q enclosed now for the second part. So, what is my Q enclosed? What I'm asking is how much charge is inside this purple circle that I drew. Well, it can't be the whole charge because that purple circle doesn't enclose the whole sphere. It must only be part of the charge. So my charge is going to be my density times my volume. And by volume, I mean the volume of the gray stuff, the volume of the charged object inside the Gaussian surface. Because I'm trying to find the charge, I know there's no charge in the white space, there's only charge in the gray space. So instead of writing out Gaussian surface, I'm just going to put GS. So what is that volume going to be? So that volume is going to be the volume of this big purple circle, take away this little white circle. So that volume is equal to 4/3 times pi times b cubed, subtract 4/3. Oops, my goodness, I said b because I saw b. It should be an r because we're doing the volume of the object inside the purple circle. The purple circle, this one has a radius of r, and I'm taking away the white space because there's no charge in that white space there. In fact, I'm just scratch all this out. 4/3 times pi times r cubed. Take away the volume of the white space because that's just empty. There's no charge on that stuff at all. A cubed. Okay, let's put this together. Density times volume. Density is rho times my volume, 4/3 pi r cubed, subtract 4/3 pi a cubed. Okay, put together my Gauss's law. So my integral of E dot dA is E times 4 pi r squared equals my Q enclosed over epsilon naught. Things simplify a little bit. My 4's will cancel because I have a 4 in every term. My pi's will cancel, and that's all I'm going to see canceling right there. So I want to solve for my E. E is equal to let's see, I've got rho over 3r cubed or epsilon naught. So this is my first term. Actually, why don't we just simplify this bit? Rho 1 over 3r cubed minus 1 over 3a cubed. Take my r squared down here. R squared epsilon naught. Okay, I'm going to multiply my rho through, and I'll bring my 3 down to the bottom. Rho r cubed minus rho a cubed over r squared epsilon naught, and my 3 is down on the bottom. You can leave it like this, or you can simplify a little bit. So that's rho r cubed over 3r squared epsilon naught minus rho a cubed over 3r squared epsilon naught. R cubed cancels with my r squared equals rho over 3 epsilon naught outside of r minus a cubed. You wouldn't have to simplify it down quite that much. Oh, dropped my r squared. But there's a simpler version you can have. Okay, last we want to find the electric field outside of everything. So I'll do one last Gaussian surface. My last Gaussian surface will be a sphere with a radius bigger than b. So there's R for my last one. Another fresh sheet of paper. Okay, so for R greater than B, I have to find my Q enclosed. My Q enclosed is the net charge on the entire shell. So there's no charge in this white space. There's no charge here. There's only charge on the gray stuff. So my Q enclosed is density times volume. My density is rho. My volume of the charged object is going to be 4/3 pi b cubed. Take away 4/3 pi a cubed. So I got this great big sphere, and I'm taking away the little sphere inside. So now I'll put that together with my Gauss's law. E dot dA, which is E times 4 pi r squared, equals my Q enclosed, rho, 4/3 pi b cubed minus 4/3 pi a cubed, and that's over epsilon naught. So my 4's and my pi's will cancel. So then I've got E equals rho over epsilon naught r squared times b cubed minus a cubed over 3. You can leave it like that, or you can simplify it a bit more. I suppose you could put your r cubed inside, of your r squared inside if you wanted to. But it's okay the way it is there now. Okay, part B. Sketch a graph of the electric field as a function of distance from the center. Label your graph clearly and show the maximum electric field. So I think I'll try and draw it on this sheet right here. Let's put in the axes. So there's R, there's E. The interesting places are where R equals A and where R equals B. And we care about the behavior in each of those places. Okay, for R less than A, there was no charge enclosed. The electric field is 0. That part's pretty easy to plot. Okay, for R between A and B, that one was a little bit strange. That was R minus something over R squared. That's a bit of an odd shape. It's definitely not linear, but it's not 1 over R squared either. So it's an increasing function with some sort of curve to it. Normally I would plot that out on Excel, to be perfectly honest. So up here at the top, where R equals B, so for R equals B, the value we get when we plug R equals B here is rho over 3 epsilon naught times B minus A cubed over B squared. Okay, that's what we get here. B. Okay, looks good. And then once we're outside the shell, it falls off as 1 over R squared. So that's that familiar form we have. On this side, if we put in R equals B here, we get an electric field. So this is our value right here from this side. From this side, it's rho over epsilon naught B squared outside of B cubed minus A cubed over 3. And we can see that this is going to be equal to the same thing. We could take our 3 out here, put our B squared in here, we get exactly the same result. So this is the maximum value. Okay, that one's definitely a bit more detailed than just doing a solid insulating shell. If you want, you could try doing this as a conductor and see what the difference would be if this was a conducting shell instead of an insulating shell.